In this worked example, we're going to see what you can deduce if you see a star that is wobbling. So let's assume we see a star and we observe that it's going in an apparent circle. What this means is we've taken pictures of this part of the sky multiple times, and sometimes the star is here, sometimes it's here, sometimes it's here, sometimes it's here. Now let's imagine that we know that this is a star much like our own sun. So assumptions, it's a star like our sun, and it's 30 parsecs away from Earth. And let's say that the radius of its wobble is 1 arcsecond, and that it takes 10 years to go around. So the period is 10 years. So over 10 years it's moved from here to here to here to here. Now what you're measuring is not actually how far it moves in kilometers, but how far it appears to move on your detector, which will be at a certain number of pixels. And if you know the focal length of your telescope, you can and the pixel scale of your detector, you can convert that number of pixels into an angle, and we'll say that angle is 1 arcsecond. What can you work out from this? Well, the first step is to work out the radius of the orbit in physical units. Presumably what's going on is you have the star, and it's going around, and its radius, we'll call it R1 here. That's what we're about to work out. And presumably it's going in circles because there is something else, I don't know, over here, say. Let's call that R2 and give this one an M2 and that one M1. And these two things will be rotating around their common center of mass. At the moment we don't know whether the second object is more massive or less massive than the first object, or whether it's further out or closer to the center of mass. All we know is there must be something there, otherwise this couldn't go in a circle. Okay, so first step, convert arcseconds into meters. Now we covered this in the first course in the series, but let me give you a reminder. Let's imagine this is the Earth, and there is some length r over here at a distance d from the Earth, and that thing appears to have an angle size of theta. Now if you measure theta in radians, the equation we did in the first course is that r equals the distance to the object times the angle theta in radians. Now in our case we know theta, which is 1 arcsecond, we know d, which is 30 parsecs, so what we want to work out is r, what is the actual physical radius of the orbit. So we get that r equals d, which is 30 parsecs. 30 times a parsec is 3.1 by 10 to the 16 meters, times the angle. Now the angle is 1 arcsecond. An arcsecond is 1/60th of an arcminute. And an arcminute is a 60th of a degree. So 1 over 60 times 60 converts it from arcseconds to degrees. And then to convert it into radians, you have to multiply by pi over 180. And if you factor all that in, it turns out that the radius of the orbit is about 4.5 by 10 to the 12 meters. So the Earth is 1.5 by 10 to the 11 meters from the Sun, so this is about 30 times bigger than that, so it's quite a big loop it's making, about as far out as Neptune is from the Sun. So it's doing the same sort of orbit that Neptune does from the Sun. But Neptune takes hundreds of years to go around, whereas this one's only going around every 10 years. So that's telling us something. What's that telling us? Well, now we've worked out this distance here, we can proceed to work out how heavy and how far away this mysterious second mass must be. So if you look in the reference notes for this week or from the videos, you find there are two equations. The first equation comes from balancing centrifugal force against gravity, and it tells us the mass of the second object equals 4 pi squared over g times the period squared r1 R1 plus R2. Now we don't know R2, we know everything else in there, so if you substitute numbers in, that comes out as 2.6 by 10 to the 7, 4.5 by 10 to the 12, plus R2 squared. So there should be a squared up there. So that's one equation. Unfortunately, we can't do much with it because it's got two unknowns. We don't know either the mass or R2 of the mysterious object. So we need another equation. That one comes from the definition of centre of mass, which is that m2 equals m1 r1 over r2. Once again, it's not an equation that will tell us anything because it's got two unknowns. We know r1 and m1. We don't know either of these. If you put numbers in, that comes out as 9 by 10 to the 42 over R2. So this again is an equation we can't solve by itself because we don't know either the mass or the orbital radius of the mysterious object. But now we have two equations, this one up here and this one down there, in two unknowns. We can, in principle, substitute one into the other and solve it, but that gives us a cubic equation, which is messy. So let's do it by the trial and error guessing method. What we're going to do is guess a value of R2 and work out the value of M2 we get from this equation and the value of M2 we get from that equation. So we'll put our guess, M2 from the first equation and M2 from the second equation. Now if we guess right, these will both give us the same mass. We've got a consistent set of R2s and M2s. If, on the other hand, they come out different, we are wrong. So what's our first guess? Well, we know that R1 is about a few tens of astronomical units, so let's guess 10 astronomical units. So an astronomical unit is the distance from the Earth to the Sun, 1.5 by 10 to the 11 meters. So this is 1.5 by 10 to the 12 meters. Stick it into the two equations, and what we get is here a value of 9.3 by 10 to the 32 kilograms, and here 6 by 10 to the 30 kilograms. Now these two masses are quite different. They're more than 100 times different from each other, so clearly 10 astronomical units was not a good bet. What we need is M2 to get larger and M1 to get smaller. If we look at the equations, we see that to get M2 larger, we need to drop R2. Likewise, dropping R2 will make M2 from the first equation smaller. So it looks like we need a smaller value. So let's try 1 astronomical unit. And now this has gone down to 5.6 by 10 to the 32 kilograms. A little bit smaller. But this has gone up to 6 by 10 to the 31 kilograms. So they're getting closer. They're now only 10 times different. Up here they're more than 100 times different. So if you drop down to 0.1 astronomical units, this, if once again you plug the numbers, you take 0.1 astronomical units and plug it into here and into there. This comes out as 5.3 by 10 to the 32 kilograms. And this comes out as 6 by 10 to the 32 kilograms. So we're very close here. We could keep on refining it, maybe try 0.11 or 0.09 or something like that, but this is close enough for current purposes. It looks like that's about what R2 is, and these two values here are about what the mass of the mysterious object is. So it appears that our Sun is doing its circles because there is something very massive. The mass of the Sun is about 2 by 10 to the 30 kilograms, so this is about 300 times the mass of the Sun. So something that's about 300 times the mass of the Sun, which is about 6 by 10 to the 32 kilograms. And because the second object is so much more massive, as the star moves around its centre of mass, the mystery object is much closer to the centre of mass. So here is only 0.1 astronomical units, whereas this is 30 astronomical units. So that's what we've got.